In this video, we will discuss our second method for finding volumes of solids, something that we will refer to as being the shell method. And first, let me introduce the idea of why we will need the shell method. So one really good reason is we will not always be able to apply the washer method. For example, let's consider the volume of the solid obtained by revolving the region bounded by y equals 2x squared minus x cubed, y equals 0, which would just be the x-axis, about the y-axis. So we're going to take the region enclosed underneath this curve and form a solid by revolving it around the y-axis. So let's think about how we would have to approach this with the washer method. So first, we would have to know what is the output here corresponding to the maximum value. Some number, call it b. And we can use calculus to figure out what that is. And then the integral that we would set up would be in terms of y values from 0 to b. Then the next thing we'd have to think about is if we pick a specific y value between 0 and b, and we form the washer there. So we take this horizontal line and we revolve it around the y-axis. When you do, you're going to create one of these typical looking washers where you have this inside smaller radius and this larger outside radius. And in terms of our picture, that inside radius will be given here, small r, and the outside radius would be this larger distance, big R. But unfortunately, with this function we are dealing with, calculating these two distances, little r and big R, is not going to be a convenient thing, and sometimes it could even be impossible. So what we are going to need is a different approach. And the different approach that we are going to use is something called the shell method. So the nice thing here is instead of having to put everything in terms of y's when we're revolving around this y-axis, we're going to keep it into x's. So the idea with the washer method was we were cutting into almost these horizontal slices and then revolving each one around the axes. In this case, we are going to cut up into vertical slices and revolve around the axes and add up the associated volumes of those vertical slices when they get revolved. So kind of the general idea with integration, we take this region from 0 to 2, you break it up into a bunch of equally spaced subintervals, and then on each subinterval we're going to approximate that associated volume. So in general what we are going to have is kind of some small rectangle here that we take and we rotate it around the y-axis. And when we rotate this around the y-axis, what we are going to do is create what we call a shell. And the idea is that if we can determine what the volume of one of these small little shells should be, then we can add up all of the volumes to approximate the total volume, and the integral over them will end up giving us the total volume. So for this shell, I'm going to try to draw it a bit more carefully here. It's a cylinder that has a bit of thickness to it. So it's almost as though we've taken a cylinder and kind of hollowed out the middle. So we think of the thickness of this cylinder as maybe being, say, a change in x, that small kind of thickness of one of these intervals. We have the height of this, which is coming from our function f of x, and then we have, in a sense, the radius of this cylinder. So we're thinking the radius is coming from how far we were from the axes that we're rotating about. So the radius would be given by this distance as long as we're thinking about corresponding to x. And how I'm going to visualize this cylinder is I'm going to cut it with a pair of scissors and then unwrap it. And when I do that, what we are going to get is maybe a more familiar looking geometric shape. What we have is a rectangle now that has just a smidge of thickness to it. So we're thinking the length of it would correspond to the circumference of our cylinder. So 2 pi x. Its thickness is the delta x, and its height is the function f of x. So putting this all together, this is going to be the shell method. So the volume here is going to be the definite integral over how the x values are varying, so 0 to 2. And we've taken this area from 0 to 2 and kind of broken it up in terms of these rectangles. And if we can think about what the volume would be corresponding to each one, that's what we're going to end up integrating. So the volume of this, what we're going to call a cylindrical shell, is going to be what? 2 pi x times f of x, its height, times its thickness. Which means what we are going to integrate would be 2 pi x f of x dx. Where note here what these things, these quantities are representing. The x that we see is representing kind of a radius of our shell, how far it is away from the axes we are rotating about. And f of x is referring to the height of one of these shells. So before going ahead and solving in this example, let's go ahead and write down the general formula that we can apply. So in general, if we're going to use this shell method, if f of x is a non-negative function, i.e. it's positive, for x values from a to b. So the picture to consider, from a to b, and we have some function y equals f of x sitting above a to b, and we're going to take that enclosed region and form a solid by rotating it around the y-axis. Then the volume is going to be given by the integral from a to b, how the x values vary, 2 pi x times f of x, where what we are thinking is, at an x value between a and b, we form this cylindrical shell. So that rectangle is rotated around the y-axis. And so it's a cylinder with a little bit of thickness, where we think of that x as being the radius and the f of x as being the height. So x is the radius of the typical shell, f of x is the height. So from the work that we had on the previous slide, the desired volume in this case was the definite integral from 0 to 2 of 2 pi x f of x dx, where f of x was coming from the height of one of those shells. So that would be the function given by 2x squared minus x cubed. So at this point, once the integral is set up, I really consider this kind of the old part of the problem. Hopefully what we're starting to feel extremely comfortable and efficient with. 2 pi is a constant that pulls out front. If we take the x and distribute it through to each term, we are going to be integrating 2x cubed minus x to the fourth. Anti-differentiating term by term, we are going to have a 2/4 x to the fourth minus 1/5 x to the fifth, and this is going to be from 0 to 2. So we plug in a 2, so we're going to have 1/2 times 2 to the fourth, which is going to be 16, minus 1/5 times 2 to the fifth, which will be 1/5 of 32. And we subtract away what we get when we plug in 0. So this ends up being 2 pi times 8 minus 32 fifths, which is 16 over 5 pi. So let's look at another example. Let's determine the volume of the solid obtained by revolving the region bounded by the curve y equals 1 over root x. Okay. bounded by the curve y equals 1 over root x. So it looks something like this. Y equals 0, which corresponds to the x-axis. Then x equals 1 to x equals 4. So we would like to take this region and form the solid of revolution by revolving it around the y-axis. And what we are going to do is use the washer method. And how I go about this is I just write down the general form of this integral. So it's a definite integral over how those x values vary. What we integrate is 2 pi, I think, something, something. Where that first something, remember, is going to represent a radius of that general cylinder. The second something is going to represent the height. So I'm thinking kind of the general form of what this integral is going to look like, and then I'm determining what quantities I have to plug in. So to do so, I just draw one of our cylinders. So if I have an x value between 1 and 4, I draw a little rectangle there, and then we take that rectangle and we revolve it around the y-axis. And looking at that, if we revolve that rectangle around the y-axis, it turns out that the radius of it has to be the value of x. So it's the distance x is from the y-axis. That distance is x. The height is determined by, it looks like, the height of the curve there. So it's 1 over root x. So it fits exactly into the situation we had on 2 slides previously where we gave the general formula. Now I typically go through this exercise of writing, kind of a blank spot and a blank spot, because we will have to modify slightly if we're rotating around, say, a line other than the y-axis, or if maybe our region, instead of being under just a single function, is enclosed between 2 curves. So it can be a bit different in terms of the sit-up, which is why we want to think of 2 pi radius height. The thought process is the most important part. So we have 2 pi, a constant which pulls out front, the definite integral from 1 to 4, and x divided by the square root of x is x to the 1/2 power. The antiderivative of x to the 1/2, we say 1/2 plus 1 is 3/2. So 1 over 3/2, or 2/3, x to the 3/2 from 4 to 1. So 2 pi times 2/3 is a constant, 4 pi over 3. We plug x into 3/2. So if we think 4 in for x to the 3/2, that would be the square root of 4, which is 2, cubed is 8, minus 1. So we have 7 times 4 pi over 3, which is 28 over 3 times pi. And that represents the volume of this solid of revolution.